let's see the Faraday's experiment. So likewise in the magnetic field, mainly that Oersted experiment, and again we can say Ampere circuital law, they are important over here, that Faraday's play a very important role. So for this case, what we are going to do, I'm just going to consider, let's say this is nothing but a closed loop, yeah, or a coil, and let's say I just connected one galvanometer. There is no source of energy over here, and let's say now there is one magnet, yeah. So when I just move this magnet in the downward direction, I found that there is some deflection in that galvanometer, yeah. So it will just get deflected towards the left, because of which, let's say the current is moving in the anti-clockwise direction over here. So now, although there is no source of, you say, energy over here, there is no battery, but still the currents flow through that your closed loop. So now how it is possible? Yeah, and again similarly you have to just do one more thing. So now when you just move that magnet away from this your coil, again you will find that there is a momentarily deflection in that galvanometer, but the current is flowing in now in the opposite direction. So let's say it is now in the clockwise direction. So what happens over here? So when you move the magnet in the downward direction, so the magnetic flux which is linked to this circuit, obviously this magnet is having its magnetic field lines. So let's say you can show in this way. So this magnet, you can just having this magnetic field lines. Again this magnetic that is field lines, so they are just going to cross through this surface area, which is nothing but your magnetic flux. So when you move the magnet in the downward direction, the flux which is linked with the circuit gets increased, yeah, and because of that the EMF is going to induced into the circuit, and because of that EMF the current starts to flow through the circuit. The same thing happens in the second case also. The magnetic flux linked with the circuit get reduced, and that is the reason you can say that the EMF is produced and the current flows. But the only, you can say, the difference between these two cases is the direction of current. In the first case it is anti-clockwise, and in the second case it is nothing but the clockwise. The same thing over here, when you move this magnet on the left side, yeah, so definitely there is a deflection in the galvanometer. That is what we can say the current flow through this galvanometer over here. So the same thing, so let's say again this is also we can just represent with the help of, let's say this is a galvanometer that has been connected across this circuit, and you just move this bar magnet, yeah. So when you just move this bar magnet towards this your coil, yeah, again it's very interestingly, so you will just find that, yeah, so again you will find that obviously the current starts to flow, yeah, so the current starts to flow through that circuit over here, yeah. So that is what we can say for this particular case. So the same thing that I can represent, yeah, so let's say I can just represent it over like this, yeah, okay. So the current, again the direction of current, let's say it is nothing but the anti-clockwise when you are moving the magnet towards that coil. And in the similarly the second case, so now you have to just take it away, yeah. So you have to just take it away, that magnet you have to just move it away from this your coil. So again for that case also you will find that the current is going to flow through that circuit, but obviously it is now in the clockwise direction over here. So that was what we called is nothing but the Faraday's experiment, where I found that I just keep that magnet moving and this coil is fixed. In the second case, either you can just keep this, obviously, so in the second case you just keep this bar magnet fixed, yeah, let's say this bar magnet is fixed, and you can just move this, yeah, and you can keep this, let's say, yeah, so either you can just do like that, yeah. So for this case, let's say you can just move this coil, yeah, so which is nothing but likewise you have to just move this coil now towards this your magnet, yeah. So for this case obviously we can say that, yeah, so obviously for this case we can say that, so this coil, yeah, so the obviously what we can say, so for this particular case now even I can just do the same thing by just moving that your coil and keep fixed your this magnet, yeah. So that is also possible for this case, so that is also possible for this case. So that is the second case where I can say that, so you have to keep that magnet fixed and you have to just move that coil. So in that case also the flux linked to that coil is going to change, and which will induce the EMF in that circuit for that. Yeah, or either take a cylinder over here, and on the cylinder we can say this is nothing but, let's say, primary coil, again which is connected to your voltage source. Yeah, again we can say there is a rheostat switch is there. Yeah, so likewise you can say, and the secondary one. Yeah, so secondary coil is also over there. Yeah, so this is how we can just connect it to the primary coil. Yeah, so you have to just switch it on. Yeah, so when you just switch it on off, you will find that, yeah, again across the secondary you have to connect that galvanometer. Yeah, so when you connect the galvanometer across the secondary, there is a deflection you will find in the secondary also whenever the flux link with it gets changed. Now that mainly happens because you are just making the primary circuit, the primary coil on and off. So because of which the flux which is linked to the secondary also, it gets changed, and that will induce the EMF in the secondary also. So that is also a principle similar to base to that of your transformer. So this is what about your Faraday's experiment.